Alright, so this will be the first of several videos for Math 1560, Calc 1 at U of L for fall 2017, where we demonstrate how to compute the derivative of a function using the definition. We'll do a few more of these in class, but it's always good to get a few extra ones to look at so you've got an idea of how these go. Now, just a reminder from the previous video, we went over the definition of the derivative, and if you want the derivative here, now this is at a point, and of course if I want the derivative as a function, I just replace a here by x and think of x as a variable. So we have these two different definitions that we can use to calculate the derivative. This one here is this is the more common version. This is the difference quotient. It's sometimes also called the Newton quotient. Okay, and that's the one that generally we work it with. But this this is an equivalent definition, and the only difference between them is that here we're setting x equal to a plus h, right? If you make that substitution, you can see that these two limits are actually the same. Okay, so let's go ahead and compute this derivative. Now, first we're going to do it at a particular point, and I can use whichever formulation I want here, but let's use the first one. So how is this defined? F prime at minus 2. So by definition, this is the limit, h going to 0, f at minus 2 plus h, subtract f at minus 2 over h. So let's plug in our function. So this is minus 2 plus h cubed, subtract minus 2 cubed, all divided by h. Okay. So of course, as you expect with any derivative, we have a 0 over 0 limit if we try to do this by direct substitution, so we've got to do some algebra. We've got a cube there, so let's expand and simplify and see where we can get. Now, I'm going to use a little shortcut here. You can, if you want, of course, with this cube here, what I'm going to do is I'm going to expand using the binomial theorem. And I'll remind you what the binomial theorem is in a later video. We're gonna start doing some derivative rules soon, and we'll see that the binomial theorem plays a role in the computing derivatives of powers generally. If you don't know the binomial theorem, you can of course just do minus 2 plus h times minus 2 plus h times minus 2 plus h, but that gets a little bit tedious. So with the binomial theorem in hand, I get minus 2 cubed plus 3 times minus 2 squared times h plus 3 times minus 2 times h squared plus h cubed. There's my cube. These numbers, there's a 1 here, right? So really I guess I could say this 1 and a 1, but we don't bother to write those 1s. Those numbers, by the way, if you learned the binomial theorem, you'll recall that those numbers come from Pascal's triangle. Okay, all divided by h. So now we try to clean things up, and we'll notice that this cancels with that, right? There's a minus 2 cubed and a minus 2 cubed. And notice that everything else in the numerator has an h left. So if I factor that out, I've got h times, well, minus 2 squared is 4, 3 times 4 is 12, minus 6h plus h squared. Okay, and I've got an h on the bottom. Okay, so what did I do there? I simplified my constants and I factored out an h from these three terms. They all had an h in them. And then we notice that this h on the top cancels with the h on the bottom. That's the part that was causing that 0 over 0 situation. And now you can see that when h goes to 0, this h will go to 0, that h squared goes to 0, and I'm simply left with a value of 12 for my limit. Okay, so let's make it slightly more interesting. Let's consider the derivative at a general point. So if I want to calculate f prime of x, where x could be really anything here, so how does this look? Well, I just proceed the same as before, only now I put x in there. So f of x plus h minus f of x over h. So I've got the limit, h going to 0, x plus h all cubed minus x cubed over h. And again, I expand that first cube using the binomial theorem. X cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. In some ways, the general case is even maybe a little bit easier because I don't have to worry about all those minus 2's. I simply have x, and that means I've got to do a bit of algebra, but I don't have to worry about the arithmetic anymore. So those first and last terms, they cancel out again just as they did last time. And I notice that these three terms, they all have an h in them. So if I factor that h out, I've got 3x squared plus 3xh plus h squared, h on the bottom. Again, I can cancel. And once I cancel, I notice that now I've got no problem. I can just set h equal to 0. This term and this term go away, and I'm left with simply 3x squared. And note that if I take x equal to minus 2 in here, I get f prime of minus 2 is 3 times minus 2 squared, which is 12, matching my previous answer. But of course, this is now, now we're ready. If somebody asks for f prime at 1, 5, 7.5, it doesn't matter. I can plug the x value in, and I can calculate that derivative at any point, and we're good to go. Just so you see how it might look if we tried to do this using the other definition. So we're going to calculate f prime of a at a general point. So what does f prime of a look like? Okay, so f prime of a would be the limit x approaching a, f of x minus f of a over x minus a. So the limit x approaching a, x cubed minus a cubed over x minus a. So I don't have to worry about the binomial theorem anymore. I don't have a binomial to cube, which is kind of nice. But I still have a bit of algebra. You can see that I got 0 over 0, and what I have to do is I have to factor that top. And just like there is a formula for difference of squares, there's also a formula for difference of cubes. And the difference of cubes formula runs like this. We take the x minus a, then we square the first term, x squared. We take the product with the opposite sign. So here it's minus, here it'll be plus. A times x, and then we square the last term. Okay, and feel free to multiply things out and verify. Right, what will I get? Here's my x cubed. I get ax squared. There's a minus ax squared. Those cancel out. Xa squared minus xa squared there. Those cancel out, and then I've got my minus a cubed. You can see that those do indeed multiply out to give you back the same thing. And now that x minus a is factored out, we can cancel it top and bottom. Limit x approaching a, x squared plus ax plus a squared. And now I can do direct substitution. I set x equal to a. I get a squared plus a squared plus a squared, which gives me 3a squared. Right? So I get that same result. It's a very different flavor in terms of the algebra, but I get to the same point in the end. All right.